Elimination reactions. Bromocyclopentane. So in an E1 reaction, same as SN1, the leaving group leaves first, generating a carbocation. Secondary carbocations are somewhat stable. They exist. Notice that pi bond is planar, and this is how you explain the racemic stereochemistry of an SN1 reaction. So let's take methanol as our solvent. The oxygen's electrons are going to abstract a proton from the cyclopentane, and the carbocation on the cyclopentane is going to abstract the electrons from the adjacent hydrogen atom, yielding a double bond and a protonated solvent. It doesn't matter if your solvent's water, methanol, whatever, it doesn't matter. And that solvent's going to form a salt with your leaving group, your bromide anion. This is a first order elimination reaction. Notice the first step was the leaving group leaving. Second order elimination. We got Zaitsev and Hofmann products and anti-periplanar elimination. So in general, you have a reactant, and then you have a transition state, and then you have your products. This is generalized to any second order reaction. So whenever you do a second order reaction on a test, make sure you show your transition state. That's very important. Okay, so this is basically just a general overview, right, where that transition state is your single peak in your reaction coordinate. That is your peak in the energy scheme of the reaction. Okay, so for Zaitsev elimination, you have a non-bulky base, like RO minus or OH minus. You know, like sodium hydroxide is OH minus. We don't talk about sodium because it's solvated by your polar protic solvent or your alcohol. Alright, so let's start with bromocyclohexane. Notice we have hydrogens which are anti to the bromine. Let's drop a bulky group on there just for clarity to define Zaitsev versus Hofmann. So let's use a non-bulky base. This hydrogen here is anti to the bromine, the one that's circled in red. There's another hydrogen which is anti to the bromine at the other adjacent carbon atom. Notice that our OH is unhindered. That negative charge can freely abstract that proton that's by that isopropyl group. And the slightly positively charged carbon, which the bromine is attached to, abstracts the electrons from the adjacent proton and kicks out the bromine, yielding the more substituted double bond. The more substituted product is known as the Zaitsev product. It is the thermodynamically more stable product. Let's look at a bulky base, like tertiary butoxide, right? We got CH3 groups all over that thing. It's super hindered. It can't abstract that proton because that isopropyl group is all in the way. But it can abstract this proton because it just sticks right out there and there's nothing blocking the tertiary butoxide anion from abstracting the proton, which is anti-periplanar, to the bromine. The electrons go to the slightly positively charged carbon center, kicking out the bromine and forming a double bond, which is less substituted. This is known as the Hofmann product. Radical halogenation. This is actually probably something you'll learn before SN1 and SN2 and E1 and E2. But let's talk about selectivity. So there's different types of radical halogenation reactions. Chlorination and bromination are two really popular examples. You're never really going to see iodination or fluorination. Chlorination is very non-selective. You get tons of different products. It's not very useful. We don't really care about chlorination that much. However, bromination is very selective and very useful. Let's look at methylcyclopentane and the bromination thereof. That bromine is always going to go to the tertiary carbon. Let's look at the mechanism. We're going to compress it just for the sake of time because I don't have time to sit here and go through all this. Bromine is split by light, creating two bromine radicals. This is known as initiation. Those bromine radicals react with hydrocarbons to form carbon radicals in HBr. That's known as propagation. The carbon radical then reacts with another molecule of bromine, propagation step number 2. And then termination, where a bromine radical reacts with a carbon radical to form the bromide. Let's look at addition reactions. We have anti and syn. Let's look at dimethylacetylene. Just for the sake of argument, we'll say that this is hydrogenation. So in anti, you get the trans molecule, and in syn, you get the cis molecule. Now obviously, hydrogenation isn't going to yield a trans molecule. Markovnikov and anti-Markovnikov. Markovnikov addition puts the hydrogens where there are the most hydrogens. Anti-Markovnikov is obviously the opposite. Let's make another chart to simplify addition reactions. So we've got syn, anti-Markovnikov, and anti-Markovnikov. Hydrogenation is always syn addition. You will never have anti-addition. Markovnikov and anti-Markovnikov are pretty much useless for this. That doesn't really matter. H2O, we're talking about making alcohols here. So for syn addition, you want to use hydroboration oxidation. For anti-addition, you want to use oxymercuration demercuration. For Markovnikov, you want to use oxymercuration demercuration. That's a two-step process. And for anti-Markovnikov alcohols, you want to use hydroboration. That puts the alcohol, the OH group, at the less substituted side for anti-Markovnikov. The addition of HX, so like HCl or HBr, is always going to be anti, and it's always going to use Markovnikov addition. You're always going to get the hydrogens wherever there's the most hydrogens. That's the definition of Markovnikov. If you add a halogen molecule such as Br2 or Cl2, it's always going to add in the anti position. Same with IBr, or sodium metal in ammonia liquid, is specific to acetylene or triple bonded compounds. And it's only going to hydrogenate one bond, and you're going to end up with the alkene, and it's going to add anti. So if you have HBr in the presence of a peroxide, it's going to add in the anti position, and it's going to be anti-Markovnikov. So your bromine is, for example, like HBr, ROOR, is going to add where there is the less substituted side of the molecule. Alkene metathesis, that's pretty much all you need to know. This basically the double bonds split and rearrange and attach to other double bonds. Alcohols. So let's just look at a little roadmap real quick about how the alcohols work. So basically here you're adding a carbon atom in red, and then in blue you're oxidizing. Primary alcohols can be oxidized to carboxylic acid, and then in green we're reducing. And we reduce using lithium aluminum hydride followed by H3O plus, or we can use sodium borohydride and methanol. Let's take a quick look at Williamson ether synthesis. So basically you have an alkoxide, a negatively charged oxygen attached to a carbon atom, and then plus some other halide. And the halide reacts with the alkoxide to give you an ether and a halide ion. Alright, so ethers. Just a couple quick things about ethers. They can be split using a strong acid and heat. That red line is that ether being split. And typically what happens is you form an alcohol and a halide, an alkyl halide. Let's look at epoxides and diols real quick. So that's an epoxide, an oxygen connected to two carbon atoms. And then a diol, right, or a glycol as it's also referred to. Basically vicinal alcohols. Alright, so if you take an epoxide and you add H3O plus, you get trans diols. Alkenes can form diols by reacting with osmium tetroxide and hydrogen peroxide, and that gives you syn diols. So that's how you get trans diols and syn diols. And you get epoxides from alkenes by using peroxy acids such as MCPBA. Alright, let's look at organometallics real quick. We're almost finished. So you have a carbonyl group. Let's take this ketone. We can take an alkyl halide and we can react with magnesium and ether to form an organometallic, or a Grignard reagent. That Grignard reagent attacks the carbon atom of the carbonyl group. It kicks the electrons up onto the oxygen, which is why in the second step you have to protonate with H3O+. So organometallics, Grignard reagents are the same as lithium reagents, and they react just like acetylide ions. Let's look at ozonolysis. Ozonolysis splits double bonds and oxidizes the crap out of them. So basically you could just cut a double bond and insert oxygens. Alright, so let's review and go through a couple problems. Let's make this compound from molecules consisting of less than 6 carbon atoms. This is a typical test question you're going to find on like a final exam or one of your later exams in organic chemistry. Alright, so we see that we have 6 carbon atoms right here in this phenyl ring, or this benzene ring. And so we want to cut this thing into pieces to make this problem a little bit easier. We want to work backwards. So first, we want to make an organometallic using that phenyl ring. We can take phenol, react with PBr3, and then magnesium and ether to get our organometallic. React with this ketone, and then with H3O+. And we pretty much built the first part of this molecule in the top left. So now we want to work on the second part, which I've circled in green. Alright, so let's dehydrate this molecule using sulfuric acid and heat, creating a double bond. There's many different ways you could go about doing this, but I tend to see things my way. Okay, so HBr-ROOR, we get the anti-Markovnikov, an alkyl halide, or alkyl bromide. We can generate a Grignard reagent from that. So let's take our Grignard reagent, and looking at our target molecule, see what's next. Let's make an aldehyde out of 6 carbon atoms, and add that to our Grignard reagent. This generates an alcohol. We can turn that into an alkyl bromide fairly easily, using phosphorus tribromide. And then we can make a Grignard reagent out of that. Grignard reagents in organometallic chemistry are very important in this class. They're very important in life. You can build almost any molecule out of these things. Okay, so what's left? We got our little cyclobutyl group. So let's make an aldehyde out of that and follow it up with H3O+. As you can see, we're just lacking 1 double bond and we're in excess of 1 alcohol. So what do? Acid catalyzed dehydration. That's it. Thanks for watching.